Hi, everyone. Abby's already introduced my talk, so thanks for coming. And I'll be talking about some of the work I've been doing during the PhD, combining my second and third projects. So just a quick introduction. So the start of the talk will be around machine learning methods that we've developed to look at characterizing distribution functions in the magnetotail particularly. So our reason for doing this is so far in space physics, predominantly we have used moments of the distribution function. However, this can be a bit limiting, and this only takes into account a small number of values. And distribution functions, however, provide us a much clearer picture of what the particles, electrons, ions are doing in space. However, this does require characterizing a large number of variables. Therefore, we've proposed to apply dimensionality reduction techniques and clustering methods to try and understand what these populations are doing. So here is just an example of a distribution that we've looked that we will be inputting into our machine learning methods. We are using cluster data from the magnetotail. And we take in about 10 years of data with a distribution equal to a dimensionality of 312. That's 26 energy bins and 12 pitch angle bins. So initially, after we've normalized the data, we first apply an autoencoder, which is used for reducing the dimensionality of the distribution. So we reduce the dimensionality by a factor of 10. This is done by first inputting the distribution, as an example here, into the autoencoder, and then passing it through a bottleneck layer, which then is used to reconstruct the original image. Then the error between the output and the input is used to optimize the lower dimensional representation of the distribution in the bottleneck layer. We can then output the bottleneck layer as our reduced dimension. This can be used for obviously dimensionality reduction, but also anomaly detection, which I'll be talking about a bit later, as distributions which have large reconstruction errors between the input and output have clearly not been able to, the autoencoder haven't been able to reconstruct these distributions due to a lack of abundance in the wider data set. So they clearly represent an outlier or anomaly. After we apply the autoencoder, we then further reduce the dimensionality down to just 3. That's using principal component analysis. We do this just because it's a lot more computationally efficient. However, we first want to apply the autoencoder in order to characterize the nonlinear structures in the data set. Once we have our 3-dimensional data set of 10 years of magnetotail data, we then apply the mean shift algorithm, which tells us how many different populations we should be seeing in the magnetotail based on the reduced dimensionality. And then once we've got this number, we apply the agglomerative clustering method, which splits the data into these different populations. So a bit about the magnetotail. Traditionally, it has been characterized, it has been classified into 3 different groups. We have the lobes, which are characterized by generally low temperature, low density, and high magnetic field strength. And then as we go towards the center of the magnetotail, we go pass through the plasma sheet boundary layer and then the central plasma sheet, which has the current sheet right in the middle. And the temperature and density increases as we move closer to the center, and the magnetic field strength decreases. So just a quick overview. This is if you want to look at the sort of structure of the machine learning method that we used. So as I've talked about it before, but we just apply the autoencoder and then set the number of epochs, batch size, etc. Validation split ratio. This was done by trial and error in order to minimize the loss values and the validation loss values, and then extract the data, apply the mean shift, and then group their different distributions into this number of clusters. So using this method and applying it to magnetotail data, we find that there were 8 different distributions, which is significantly different to the 3 which moments of the distributions have found. And this 3D plot here visualizes all the different distributions from the 10 years of data into a 3D space. And then we've been able to cluster these into 8 different groups using the agglomerative clustering algorithm. And as you can see from this, it's done quite well in distinguishing between different structures. And that's one good thing about agglomerative clustering, is it's able to group together structures which are quite non-spherical and complex. K-means, for example, which is commonly used, would just sort of drawing straight lines across this. And we were seeing lots of varied full distributions being mixed up in the same clusters. And you can also see that there doesn't seem to be any mixing across boundaries between clusters. And another thing later on is we do have a few distributions that are a lot further away. So these would represent outliers that we need to look into. We've also shown that from the histograms using Gaussian mixture matrices, the probability of distributions belonging to a certain cluster is very high for most of these points, which assures us that the agglomerative clustering does seem to be working when clustering this data. So taking the average distribution from each of the clusters, we can create these 8 different plots. This shows us what I've shown earlier, the energy and the pitch angle and the differential energy flux for each population. And we find that there's quite a large spread across these different average distributions. You get some which have very low temperatures, and in this case, high densities in the parallel and anti-parallel directions. You also get some where there's very low densities and low temperatures, and you also get some where there are high temperatures and sort of medium densities. So looking at this, we can try to start characterizing and explaining what these different populations would represent based on the different parameters. So taking the temperature and density and plasma beta, for example, and from that we can attribute certain distributions to what we already know about the magnetotail. So for example, this one is particularly the lobes, this one's the plasma sheet boundary layer. However, what is interesting is there are 6 distributions that we find within the plasma sheet, which shows that there's actually quite large variations within the plasma sheet based on all of the anisotropy, temperature, density, etc. And that's something we've been able to distinguish with our autoencoder and clustering method. We've also compared it to the ECLAT dataset, which just labeled the plasma sheet into the magnetotail into plasma sheet, a boundary layer, and lobes, and we found that we are in very good agreement for most of these labels as well. As you can see here, I've just plotted the clusters against temperature and density, and we see they do generally seem to stick together in their groups. We get obviously some elongations, however, they are clustered very close to each other. So then moving on to the outlier distributions. The reason we started looking into the outlier distributions is we wanted to find evidence of the tearing instability. Now, this is a mechanism responsible for predominantly and widely regarded as being responsible for magnetic reconnection in the magnetotail, a process where magnetic energy is converted into kinetic energy. Magnetic reconnection is obviously important in a wide variety of areas, so that's why we wanted to see if we could provide evidence, in situ evidence of the tearing instability. However, it is known to be very elusive and short-lived, transient, so that's why we thought an outlier detection method using the autoencoders would be quite useful. So this allowed us to find 15 separate tearing events in the 10 years of data that we looked at. So I'll just talk a bit about that now. So as you can see, this is reconnection, where you get current sheet thinning in the magnetotail during the expansion phase of the substorm, and then at a certain point, these lines reconnect, and then electrons and ions are transferred back down towards the Earth. So this is one particular example of a tearing instability that we found. So in terms of the outlier distributions that the autoencoder outputted, that's this one here. So the autoencoder found 15 groups of these different distributions, with a few of these for each individual event. And as you can see, they're very distinct from everything from distributions either side of it, and also from the main populations, because of the very high anisotropy, as well as the energies that the anisotropy is observed at. So once we found these distributions, we wanted to verify that we are looking at a tearing event. This was using information from simulations about tearing instability, and also magnetic field instability criteria as well. And also we wanted to see if we could then observe reconnection subsequent to these observed distributions. So looking at this parameter plot here, we have B, which represents the tearing instability, and we find that after this is observed, we get an increase in temperature, which is expected from the simulations, and then it's followed by an isotropization, where you get a higher temperature distribution after the tearing instability than before the tearing instability. And it also occurs during magnetic field measurements that are within the instability criteria. Subsequently, we do then observe a reversal in the normal magnetic field component and the parallel velocity component, which is one indicator for magnetic reconnection. I'll talk about further identifiers for that in a second. However, this is just showing you a plot we made to illustrate the spacecrafts flying through the flying through the tearing region and the magnetic reconnection region. As we can see here, we have straight magnetic field lines, and then we start to observe these higher increases in temperature, and this is where we observe the tearing instability. We then go through and observe the reversal as attributed by the flip in the BN and VL components, and then carry on to the high temperature region. So here we have a magnetic quadrupole plot showing the out of plane magnetic field and how we observe these quadrupole signatures. So we have a anti-parallel and parallel gradient between the negative and positive VL. So this indicates that the spacecraft is observing this quadrupole signature around the tearing events, making us more sure that there is this that we are observing reconnection. And this is just shown as well by the histogram plot, showing that the dominant outer plane magnetic field is dominant for the particular regions that we're interested in. We can then, once we've found all the different tearing events and linked it and made sure that they are definitely tearing events, we can try to understand a bit more about the plasma dynamics, which we couldn't have done without locating these with the outlier distribution. And we can obtain things like the Lundquist number and the magnetic diffusivity, as well as the resistivity, to try and better understand under what conditions the tearing instability arises. And we can see here, we can plot the sort of alpha and growth rates of the tearing instability, as well as show exactly what Lundquist number conditions are required for the tearing instability, as well as current sheet width and alpha speeds. So in conclusion, we've proposed a new method in order to characterize space plasma regimes using machine learning techniques, in particular dimensionality reduction and clustering. And with this method, we've been able to distinguish between different populations in the plasma sheet in what was usually considered to be one population. However, we found distinct differences between different groups within the plasma sheet population. We then adapted our autoencoder method to output not the main populations, but outliers, in order to understand more of the physics that's going on in the area. And this has given us insight into instabilities and energization of the surrounding plasma and temperature, and will hopefully shed more light onto what's going on in the area and how it's important with regards to substorms and reconnection and aurora. Right, thank you.